high-degree polynomials, equations with powers like x to the 16, things that seem incredibly daunting. Usually we end up relying on approximations, which are, just that, approximations. But what if there was a way to get the exact symbolic solutions? That's really our mission today. We're going to explore a frankly groundbreaking method that seems to completely redefine how we approach these challenges. And it's all thanks to something called Ezoudi's theorem.
Yeah, it's really quite something. What's fascinating here is how this new method gives us a precise analytical answer. I mean, for problems that have historically stumped even the best classical approaches. And we're going to demonstrate its power today. We'll tackle a specific and pretty formidable degree 16 polynomial equation, show how it works in practice.
Okay, so exact solutions, that's the goal. But maybe first, let's unpack why these high degree polynomials are such a headache for the traditional methods. What makes them so tough?
Well, that's a great starting point. Most classical methods, think things like Newton's method, they fundamentally rely on numerical approximations, iterative processes. And while they're useful, I mean, really useful in many contexts, they do come with significant drawbacks.
Like,
Well, they can be quite error prone, for one, especially as the equations get more complex. And maybe more importantly, they can't guarantee exact values. You're always left with a close enough answer.
right, not the precise mathematical truth.
Exactly. And this ties into established mathematical understanding, too. We have things like Abel's theorem, which for centuries has suggested that certain polynomials, specifically degree 5 and higher, just cannot be solved using radicals.
So using just standard arithmetic and roots.
Precisely. Can't express the roots that way. And this has kind of set a boundary on what mathematicians thought was even possible for finding exact solutions for these higher degree beasts.
Okay, so the takeaway for a long time has been some problems just don't have those neat, exact answers we might want. We have to settle for almost.
That's pretty much been the standard view. But Ezouidi's theorem comes at it completely differently. It doesn't try to fit into that old framework. It's a method that, well, it claims to demonstrate that even these polynomials, the ones Abel's work might suggest are tricky or impossible with radicals, can potentially be solved exactly, symbolically.
Okay, now that's interesting. This isn't just a minor adjustment, then. It sounds like a complete redefinition of the problem almost.
It really is. It sort of bypasses the limitations that have traditionally boxed in classical algebra and those numerical methods we talked about.
So no more close enough.
That's the idea. Instead of approximations, Ezouidi's theorem works by revealing the exact symbolic roots. And it does this through a structured, recursive process, like building blocks. This ensures the roots we get are absolutely precise, not subject to those little rounding errors or the other issues that creep into numerical calculations.
All right, let's put it through its paces then. You gave us a specific example, this degree 16 polynomial. Let me see if I have it here. Px equals, well, it's long, x to the 16 minus 1615x to the 15 plus 120x to the 14 and so on down to a constant term of plus 3000 equals 0. It looks like a monster. How does Ezouidi's theorem even start to tackle something like this?
Okay, so the first step is actually quite clever. We express the polynomial not just by its numerical coefficients, but in terms of a set of symbolic coefficients. Let's just call them S sub r, okay? So 0r, S1r, S2r, all the way up to S15r for degree 16.
Symbolic coefficients, like placeholders.
Kind of, yeah.
Yeah.
But the core idea is that we can recursively calculate these coefficients based on the original polynomial's term.
Recursively. So each step depends on the one before it, building it up piece by piece.
Exactly right. And the crucial part is that every single one of these sub-bar coefficients is determined symbolically, algebraically. There's no numerical approximation anywhere in this stage. The theorem provides a specific formula for this recursion. It looks a bit complex on paper, involving things like binomial coefficients and terms from the original polynomial, and importantly, the previous S coefficients you just calculated.
Okay, so it's a defined process.
A very defined process. Now, here's where it gets really interesting for this specific polynomial we're looking at. When you actually apply this recursive calculation, well, something quite remarkable happens. Most of these symbolic coefficients, from 0r up to is6r, and then again from C to R all the way up to 6 bar, they all surprisingly turn out to be exactly 0.
Wait, really? So a whole bunch of the complexity just vanishes? That sounds almost too good to be true.
It's pretty amazing when it happens. It's a feature of how the theorem interacts with the structure of this particular polynomial. So all that complexity collapses. We're left with just two non-zero symbolic coefficients, S7r and S15r.
Only 2 out of 16.
Just two. And we can calculate their exact symbolic values. S7R turns out to be minus 12, 12 at 860 times 16 to the power of 8,
Hmm.
an exact value. And S15R is 159 times 16 to the power of 16. Again, precise.
Okay.
So that huge, scary 16th degree polynomial we started with, it drastically simplifies. It becomes just x to the 16 plus S7R times x to the 8 plus S15R equals 0. Or plugging in the values, x to the 16 minus 12 to the 860 times 16 to the 8 times x to the 8 plus 159 times 16 to the 16 equals 0.
Wow. Okay, that is a huge reduction in complexity. It looks almost like a quadratic equation, but
Huh.
with powers of x to the 8.
Exactly. It's structurally much simpler. Now, how do we get the final roots for x itself?
Yeah, that's the question.
We continue applying the recursive relationships derived from the theorem. There's a way to solve for x to the power of 8 first. It involves using another derived value, let's call it S1R prime, which we calculate directly from those non-zero S7R and S15R values we found.
So, still following the theorem steps.
Still following the steps, all symbolically. The beauty is that the roots just emerge from this process, step by step. And for this specific polynomial, the exact symbolic roots for x are found. They end up being expressed in terms of complex exponentials and radicals specifically, eighth roots in this case. Something like, well, the exact form involves the square root of a calculated value involving S7R and S15R, and then taking the eighth root of that, combined with terms representing rotation in the complex plane to get all 16 roots.
Complex exponentials. So, we get all the roots, including the complex ones.
Every single one. And crucially, without any numerical approximation at any stage. The final form gives you the precise algebraic expression for each root.
This is, well, it feels like a really big deal. For problems we previously thought were only solvable approximately, this suggests we can actually find the exact answers.
That's precisely the significance, yes. It's about obtaining these exact symbolic solutions. They aren't susceptible to the rounding errors, the instability, the limitations that, inevitably plague numerical methods, especially for complex systems.
So, thinking about practical applications, where does this matter most? Engineering, physics.
Absolutely. Think about fields where ultimate precision is critical. Cryptography relies on the difficulty of certain mathematical problems. Advanced physics simulations, modeling quantum systems perhaps. Complex engineering designs, maybe in control theory or signal processing. In any area where a tiny numerical error could potentially cascade into a massive failure or incorrect conclusion, having an exact, unambiguous algebraic form for a solution it's transformative. It really pushes the boundaries of what we can analyze with certainty.
It's really a testament, isn't it, to how even very established ideas in mathematics, things we've accepted for centuries, can still be challenged and, well, maybe even fundamentally redefined by new perspectives, new approaches.
Indeed. It really demonstrates that there's always more to uncover, more to learn, and that genuine innovation can completely shift our understanding, even of seemingly fundamental principles. It's exciting, really.
What an incredible deep dive that was. From problems that seemed, almost impossible to solve exactly, to finding precise analytical solutions. It really makes you wonder, doesn't it? What other long held mathematical truths or even assumptions in other fields might just be waiting for a new way of thinking?
It's a great question. It shows that the journey of discovery is far from over.
So, as you go about your day, maybe think about this. Where else in life or in your work do we sometimes settle for approximations for good enough when maybe, just maybe, a precise exact answer is actually achievable? Perhaps just waiting around the corner for a different approach to reveal it. Thank you so much for joining us on this deep dive. Until next time, keep exploring, keep questioning, and definitely keep digging for those precise answers.